Good afternoon. My name is Jonathan Brew, and today I will be walking you through the GreenPay Security Policy, which is a formalized set of standards built on the secure coding practices our team already uses every day. As GreenPace grows, making these practices explicit and shared across every developer is how we stay ahead of threats. Our guiding philosophy is defense in depth. Rather than relying on a single security control, we layer multiple defenses so that if one layer fails, others remain in place. This policy doesn't introduce new burdens. It standardizes what our best developers are already doing and closes the gaps where inconsistency creates risk. This matrix maps our documented standards against their likelihood and priority. Standards like Standard 002 written in C, Standard 031 in C++, and Standard 020 written in Java sit at the top. They are both likely to occur and are a high priority to address. Lower probability items like Standard 10 in Java and Standard 040 in Java are still tracked, but they don't demand the same immediate attention. This matrix tells us where to spend our energy first. Our policy is organized around 10 guiding security principles. At the foundation, validate all input data, heed compiler warnings, and keep code simple. We enforce least privilege and default deny to limit the blast radius of any breach. We sanitize data before it reaches external systems, and we practice defense in depth at every layer. From a priority standpoint, Standard 020 Java and Standard 050 C++ are our highest priorities. These directly govern input validation and memory safety. Medium priority items like Standard 031 C++ and Standard 060 C++ cover exception handling and container safety. All standards together form a consistent baseline every developer on the team follows. Encryption is addressed across all three states of data. At rest, we encrypt stored data so that even a successful breach yields nothing usable without the keys. In flight, all data moving between our backend and front end is protected against interception. In use, we protect actively processed data through proper memory management and rigorous input validation. Together, these policies ensure data is never left exposed regardless of where it lives. Security also depends on who gets access and what they can do. Our AAA framework addresses this. Authentication verifies identity, ideally through multi-factor methods. Authorization controls what an authenticated user can actually do, enforced through role-based permissions paired with a default deny posture. And accounting means we log everything, giving us early warning of suspicious behavior and a forensic trail if something goes wrong. We catch vulnerabilities early through automated testing. Our unit tests, some examples of which are shown in the following slides using Visual Studio C++ framework, verify critical behaviors. This example tests that a vector container's reserve function doesn't silently expand the collection size. This ensures that you can add at least the specified number of elements without triggering the internal memory reallocation, protecting a system's memory and maintaining application performance. This test illustrates how to test for a container's maximum size exceedance that could result in the system crashing or exploitation. It ensures that a linked error exception fires when a container limit is exceeded, which should be explicitly handled. This example tests that resizing correctly reduces a collection to 0. This ensures that an application can properly handle memory management and doesn't lead to memory leaks or undefined behaviors. This last example illustrates how to test that an application throws an out-of-range exception on invalid index access. This tests that an application handles errors gracefully, remains stable, and eliminates a potential security vulnerability. These tests make our security assumptions explicit and machine verifiable, not just understood by the developer who wrote the code. This diagram illustrates the DevSecOps pipeline. After pre-production and before each production update, automated security testing should be performed to ensure that our product is as secure as we can make it before reaching our clients' hands. To support continuous security, we embed testing into our DevSecOps pipeline. Shown here are some examples of automated tools that can be used. Veracode provides cloud-based static analysis. Checkmarks uses AI to surface and prioritize vulnerabilities. OWASP Zap automates web application scanning as a free, open source option. Together, these tools shift security left, finding issues during development, not after deployment. The business case is straightforward. IBM research shows that vulnerabilities cost up to 30 times more to fix after release than during development, and rework already consumes 20 to 30% of IT budgets. Acting now protects our customers, protects our release schedule, and saves money. No policy is ever truly complete and lasts forever without change. Looking ahead, we recommend regular policy audits, continuous adoption of new automated tools, full continuous improvement and continuous development integration, and periodic third-party security reviews. Outside consultants are especially valuable for preventing complacency. Fresh eyes catch what internal teams can come to overlook. To close, keep code simple. Design with security first. Treat all incoming data as hostile until proven otherwise. Handle every warning and exception. And remember, moving to DevSecOps is a culture change, not just a tooling change. Follow the policy, and if you see something that doesn't look right, say something.